Hey guys, this is Cannon. Today we're going to look at this LeetCode problem, number 2366, minimum replacements to sort the array. Let's take a quick second to see what we're dealing with here. So we've got an integer array called nums. We're trying to make nums non-decreasing, which is, each item is less than or equal to the item immediately to its right. That's what that means. We can look here at the constraints. All the numbers are going to be positive, and we have 100,000 at most, quite a few. So in one operation, we can turn any number into two numbers in the same spots that sum to the original number. So we turned 6 into 2 and 4. Let's take a look at an example to see how that's going to work. But the goal is to return the minimum number of operations to make the array softly ascending or, non-decreasing. So let's take a look at an example. We're going to use this 7, 6, 2, 0, 4, or I guess 20, 2, 0. All right. Let's draw this out. 7, 6, 24. So remember, in one operation, we can turn any number into two numbers that are that sum to the original. So the way that I thought about this is really what we're trying to do is we're trying to do the least amount of work possible, which means that we always want to be creating numbers to the left of the number that we're currently working on that are just under this number. So for example, we wouldn't want to turn 20 into 1 and 19, because then we'd have to turn 19 into into a number that was eventually smaller than or equal to 4. So what I think makes more sense is let's turn 20 into 4 and 16. And then let's turn 16 into 4 and 12. And let's turn 12 into 4 and 8. Let's turn 8 into 4 and 4. So if we kind of clean up this tree, we basically, by using 4 operations, we've turned 20 into 4, 4, 4, 4, and 4. This is actually the best way to split 20 up such that every item we split it up into is less than or equal to 4. If we take too much, right, if we were to turn it into 1 and 19, then first of all, this 19 is larger than 4. So we'd have to trim that down. And then also, if you think about it, all of these numbers to the left that we're going to we're going to have to get all those numbers to the left to be smaller than or equal to 1, which is going to be extra work because 6 has to go into 1 and 5, and then 5 has to go into 1 and 4. So we end up doing 5 operations to get 6 small enough, when if we use 4s instead, then 6 only has to get under 4 instead of under 5, or instead of under 1. So let's now look at 6. And this is interesting because now the smallest number we have is 4. And 6 doesn't go, we can't split 6 into even piles of 4, right? The best we could do is 6 into 2 and 4. But look here, the problem is now 7 is going to have to be split into numbers that are smaller than 2. So that's no good. We want to split up 6 into even-ish piles, meaning piles that are, where the smallest and the largest element in the pile only differ by 1. We want to use 3 and 3. The reason is because that's just as expensive as splitting it into 2 and 4. And we give ourselves flexibility because now 7 only has to be split up into piles that are smaller than or equal to 3 instead of smaller than or equal to 2. So kind of at each number, we're giving us ourselves additional flexibility later down the line by creating piles that are basically as large as possible while still fitting under the number previous. So let's put those in 3 and 3. And then 7, this is interesting because now, we know that all the piles have to be smaller than or equal to 3, but 7 doesn't equally go into piles of 3. So what we're going to do is we're going to create a pile that is of size 3, and then we're going to create 2 piles that are size 2 and size 2. So 2 plus 2 plus 3 is equal to 7, right? 3 plus 3 is equal to 6. 4 plus 4 plus 4 plus 4 plus 4 is equal to 20, and then 4 is by itself here. So let's actually think about how many operations that took. So 20, right? We first had to split it into 16 and 4, and then that quantity into 12 and 4. So we used the cost to split 20 up was 4. The cost to split 6 up is 1. We only had to use one operation to split it into 2 parts. And then 7 is 2, because we had to split it into 5 and 2, or 3 and 4 or whatever, and then 4 into 2 and 2. So the cost is equal to 7. Okay, so now that we kind of have an intuition where we basically want to split each number into piles that are as close to each other as possible in size, so we don't have waste where we're splitting 7 into 6 and 1, because 6 is that's just not a great way to partition. We need to split each number into even-ish piles that are at most the previously smallest number we've seen. And then we want to figure out how expensive that was. So we're going to basically think about a helper function called f. And f is going to take a number n and a minimum like previously seen number k. So for example, here, we would say f of 20 and 4, because 4 is the number we'd seen previously that was the smallest. And we need f to do a couple things. We need f to return the cost of splitting 20 up into numbers that were smaller than or equal to 4. And then we want to figure out the smallest number that we split 20 up into. So let's think about that as returning a tuple. So it's going to be the cost. So let's just write the pseudocode here. So the number of piles is going to be the ceiling of 20 divided by 4. And that's equal to 5, because 20 divided by 4 is 5. And then the cost of splitting 20 up into piles of 5 is into 5 piles of 4, excuse me, is going to be 4, because so cost is equal to 4, because first we split 20 up into 4 and 16, then 16 up into 4 and 12, then 12 into 4 and 8, and then 8 into 4 and 4. So each time we do a split, right? 1 split, 2 split, 3 split, 4 split. So we have 4 times we split. And then the other thing we need to think about is what's the minimum seen, what's the smallest number that's in these piles. And that's going to be let's call that smallest pile, or min pile. That's not how you spell pile, huh? Min pile. And that's just going to be the floor of 20 divided by the number of piles. And we can think about that, right? If we let's say that we had f of 7 and 3, right? The number of piles is 3, right? Because it's going to be 7 is into 2, 2, and 3. So there's 3 piles. The cost is going to be 2. And then the minimum pile is going to be the floor of 7 divided by 3. 7 divided by 3 is, let me grab my calculator. It's hard to do math in your head while you're trying to record a video. 7 divided by 3 is 2 and a little bit. If we floor that, it's going to be 2. And we see that works out because the smallest pile is 2. Anyway, so that's why we have to have a floor here, because if not, then it would be the smallest pile would be 2.3, but we already said we're splitting it into, integer piles. So then this function is just going to return, it's not an R, it's going to return cost and min pile. The reason we're returning the min pile is, like, for example, when we run f of 6 and 4, which we'll run once we're on this element here, we know the previously smallest seen element is 4, but we want to now know, like, what's the smallest element that we have created now, and that's going to be 3. So hopefully this makes sense. As we go through the algorithm, we're going to be keeping track of a number called min seen. That equals 4 at the beginning, and then result, which is 0 to start. I'm gonna clean this up. Let's kind of run through the operation of this algorithm and see how it works. Now that we have the pseudocode for this function f. So we start here. We first check to see if this number is smaller or is bigger than the number we've previously seen. Like, do we need to break this down? We see that it's the same, so we don't need to break it down. 20 is definitely bigger than the previously, smallest seen. So we need to break 20 down. If we run f of 20 and 4, we see that gives us the cost is 4 because we're splitting it up into 5 piles. And each time we do a split, we end up, we start with 1 pile. Each time we do a split, we create 1 more pile. So we started with 1 pile. We want to get 5 piles. So the cost is 4. And then the smallest element of the smallest pile is going to be 4. So we set min seen to this number, the smallest pile created, and then result is going to, we're going to add 4 to the result because it took 4 cost to split this 20 up. Now moving on to 6, we run 6 through f, still using, this min seen here. And that is equal to, the cost is 1 because we're splitting it up into 3 and 3. And the smallest pile is going to be 3. So we now change this to 3 and we add 5 to result we add 1 to result, making it 5 because it took 1 cost here. Now we have to run f of 7 and 3. And if we do the math, we already did that math here. We have 3 piles. The smallest pile is 2. And the cost is 2 because we started with 7. 1 split gets us 3 and 4. And then 1 split on 4 gives us 2 and 2. So this is going to be, the cost is 2. And the smallest pile is 2 as well. So now result, we add 2, 2, oops. So we end up with 7, and the smallest pile we've seen is now 2. Okay, we reached the end of the array. So we just need to return this number, which is the total cost we spent to break this up. Now it's interesting. We can think about like, we don't actually have to split up these numbers. We don't have to change the array because we already decided that this approach we're doing is optimal. And so, we only care about the final cost. We don't care about the intermediate states of this array. So let's move back over to LeetCode and actually code that up. Let's do that. And then let's move this to its own window if I can. Okay. And then let's center in on this function. So, okay. Let's define, actually, I can actually give myself a little bit more room over here. Excellent. Okay. So we can define our variables that we're going to use. We keep track of two things: result, which starts out as 0, and min scene, which is going to be the rightmost number of nums. And then at the end, we're going to return result, whatever that is. Okay, perfect. Let's write that function f first. So f takes a number n and a number k. First, we say that the piles is going to the number of piles is going to be math.ceiling n divided by k. And then we need to figure out the cost of dividing n into piles, right? Into this number of piles. And we already talked about how that was the cost is piles minus 1, because we start with one pile, and each time we use a unit of cost, we're adding one more pile. And then the smallest pile is going to be the floor of n divided by piles. So, and it does not, oh, we need to use the math module. Okay, and quickly, we talked about how that works. If we have 20 and we have 5 piles, then we're dividing it into into piles that are at least, at smallest, going to be piles of 4, because 20 divided by 5 is 4. And then we talked about how if we have 7, right, we have 3 piles, 7 divided by 3 is like 2.3. And then if we take the floor of that, that's 2, meaning that the smallest possible pile we'll create is going to be 2. So let's just return the cost and the min pile out of f. Okay. And then let's actually iterate through the array from the right to the left. So we'll do that like this. If you haven't seen this before, this is how you iterate from one side to the other, from the right to the left. All right. So first of all, if the number that we're on is smaller than or equal to the previously smallest seen number, then we just want to set, we can never make that number larger, and so we have no control over it. And so we're just going to set the minimum seen to be that number. So if nums of I is smaller than or equal to min seen, then min seen is going to equal nums of I. Okay. And then we'll continue out of that. All right. If it's larger, then we want to figure out what's the cost and smallest pile we get when we run f, which is the partition function. So we'll say cost and then smallest pile is equal to f of nums I and min seen. Then from here, all we have to do is say that min seen is equal to the smallest pile. and result has cost added to it. All right. Let's see what we get here. We should be getting 7. And we did. Now this is the moment of truth. Let's run it for real on the entire. Perfect. All right. So this is, 33%. That looks slow, but if you look at the details, we're kind of right in the middle of these fast solutions. If we were all the way over here, maybe that would be a problem, and we'd be slow. But we're kind of right in with all of these different fast solutions, and so sometimes in LeetCode, you run the program a few times and just random stuff, comes up and it looks slower or faster. So this is an efficient solution. Hopefully we kind of understand the intuition behind it, and I appreciate your time. Check back for more LeetCode videos like this, where I explain kind of in depth what your thinking should be. Hopefully we can get some of those out as well. I guess as an end, right? And if you're doing this in an interview, which honestly, this would be a pretty hard one to do in an interview, because it takes, 20 minutes to figure out a solution and to code it up. But if you were in a long technical interview, they would ask, what's the cost? What's the algorithmic complexity of the algorithm, right? So this is actually O of n, because we're only seeing each element one time. There's no nested loop, and so it's just going to be order n. Now you could say that for extremely large numbers of n, extremely large numbers in nums, but that's negligible, because we're guaranteed that they're a fixed size. They're only going to be, it's a 32-bit number, so that's negligible. Anyway, thanks, and have a good day.